Okay, assalamualaikum and good morning. So, let us immediately start our lecture since we have missed the Monday lectures. So we should be doing a little bit faster this time. Let me just recall what we have done in the previous lecture. We have gone through what we call the rotation matrix, and essentially from the form that let me go back up a little bit, from the form that when you do a rotation, the length of vector is always the same, okay, and based on this what you call identity, one can actually obtain some conditions on the rotation matrix. So these are the conditions that we had previously, and also there's another condition where it was supposed to be 0. Okay, so then one can actually identify the A, B, and C and D to be essentially from your trigonometric function. And this is good in some sense because it makes the connection to the parameter that gives you the rotation. Okay, in this case, the parameter is essentially your angle theta. Okay, so this will be your parameter of rotation. And we also remember that there are two different types of rotation that we can think of. Either you think of your vector as being rotated or your axis being rotated. So they are slightly different in the rotation matrix. So I think probably you have seen this before, the one with the minus sign on top on the first row will be corresponding to the what we call the active rotation, and then the one with the minus sign theta at the second row, that will be a passive rotation. So one just needs to you can actually figure out from some kind of geometric transformation, but it's best for you just to memorize this until you need to understand a little further. Then you probably want to go back to the first principle. So the other thing that we have also mentioned at the end of the lecture is essentially the orthogonal matrix. Okay, the orthogonal matrix, which is representing in this particular case the rotation matrix, obeys this condition. Okay, and if you take this particular equation and take the determinant of the whole equation, then you will be obtaining this particular identity for so remember that this is what we call orthogonal matrix. So the orthogonal matrix will have to obey this particular determinant identity. It's either the determinant is a +1 or -1. And of course, you have actually seen if you take the determinant of this 2 by 2 matrix, here is a passive rotation, you get cos squared plus sine squared, which is equals to +1. Okay, so in other words, you can identify the rotation matrix with the matrices that has determinant m equals to +1. Okay, +1. So here, because of this what we call condition, that the rotation matrix must have positive unit determinant, then we call this as special orthogonal matrix. Okay. Special being referring to the fact your determinant is +1. Okay. Now, one can ask what would be the case. Your orthogonal matrix could be determinant m minus 1. Then one can ask the question, what is a matrix with determinant m minus 1? Well, we take the simplest case for, in this particular example. Here you can take this matrix, okay, which you can actually see this will give you minus 1, okay, determinant. And what does it do to a vector? Okay, the two-dimensional vector here, x and y. What does it do? It simply gives you, okay, your x doesn't transform, but your y transform to a minus y. Okay, so in other words, x is going to be fixed, and this is essentially the action of a reflection about the x-axis. Okay, so you have this as your, say, what you call point over here, xy. If you reflect it about the x-axis over here, then you know that it's going to be somewhere here, and this will give you x minus y. Okay, so in other words, now we have the understanding that whenever you have a orthogonal matrix with determinant minus 1, then there must be some form of reflection inside that transformation. Okay, so here's an exercise that easy for you to do. Just identify the matrix for which instead of reflection about the x-axis, you have a reflection about the y-axis. There's something going on. I'm still with you, right? By the way, I didn't check out. You saw my lecture notes, right? Okay, great. Okay, so over here, there you can actually try to find out easily. Okay, to think of a reflection axis, then this will give you xy will be reflected about the y and to give you what minus x y. So you can easily identify what matrix that gives you that. And these are simple examples where you can identify almost immediately. Okay, but there are cases where you probably have to think a little harder. Okay, so here's two matrices which are orthogonal. So one of them is essentially a rotation over here. So you take the determinant here is plus a quarter and then plus a 3/4, okay, because you have a half here. Okay, so that gives you a determinant 1, and here is the determinant minus 1, and then you multiply these two together, and if you check this matrix, the product of these two matrices, the orthogonal matrices before, then you'll find that this should give you a determinant minus 1. Okay, then you might want to ask, okay, if this is determinant minus 1, then it should correspond to a reflection. Okay, so one would simply ask what kind of reflection it's supposed to be. Okay, so the best thing is to work out the example in detail over here. So you might want to find a general reflection. Let me just draw this. A general reflection is not necessarily just about x-axis or y-axis. It could be something about some arbitrary line. Okay. So this could be your reflection axis. So one needs to know what would be what you call what would be this reflection axis supposed to be, or what is the equation of this line? So one of the things that you have already seen before, if it's a reflection about x-axis, then your x coordinate doesn't change, y-axis, your y coordinate doesn't change, okay? And you can see that, okay, in a way, I would just need to know a point on this line, okay, which I know under the reflection about this axis or this line, this point will not change. So I construct an equation that that sort of does that. So here is your matrix C, and then it multiplies position vector here, which I assume to be a point on this particular line. So it's an arbitrary x and y, but it's supposed to give you the relationship of this particular line. And because of that, I would also have this to be equals to xy, because it doesn't transform under the reflection of this, it doesn't transform the point itself. Okay, so one multiplies this out and then try to solve the equation. So you get essentially two equations. You get 2 by 2 times 2 by 1 matrix that gives you a 2 by 1 result, and that gives you two equations, and essentially these two equations are just the same equation, which gives you what you call the equation of y equals to minus root 3x. So one could actually okay, try to plot this out and then see what happens with reflection about this line. So one can start now. Okay, given matrix C, I will now start to think of any arbitrary what you call vector that points it's not necessarily on the reflection line, but I will be able to get what this new reflected point about that line. Okay, so these are just things that you could actually do as an exercise for you to find out, and then you can draw them. Okay, but rotation under 2 dimensions have it's not the most general rotation. You probably have seen expression involving special rotations in 3D, okay, which we will start to give now. If you think earlier, what happens when we had the 2-dimensional case, okay, you have this rotation over here, okay, where's the rotation axis? The rotation axis is about what you call it's a line sort of coming out from the piece of paper. Okay, so in other words, you have a z-axis somewhere, okay, sort of pointing out. Okay, so over there, of course, the rotation axis being the z-axis, so I can think of now in this way. Here's your x and y, and then here's your xy plane earlier, so this gets rotated in a way, okay, to this point, but you'll see that any points on this line of the z-axis will not be rotated or will not be transformed, and it will have the same coordinates. Okay, so in other words, the 3-dimensional rotation, the 2-dimensional rotation here, this is x and y here, when you think of it as a 3-dimensional rotation, okay, in this particular picture here, so this is z-axis, then it will have this particular 3 by 3 matrix form with your z part, okay, should not be transformed. So if you just multiply this r with x, y, z, then you can see that, okay, you will get your transform x and y, but your z is the same as the the previous z. Okay, so this is it's still a two-dimensional rotation in some sense, but it's being embedded in a bigger space of 3 dimensions. Okay, so instead of thinking of this picture in a plane, and I can think of that plane being situated here, and I will have a 3-dimensional rotation. Okay, so okay, now one can ask, okay, if that is a rotation about the z-axis, what about the x-axis and y-axis? Of course, then it's quite easy to generalize this. For the x-axis, say the rotation about x-axis, then your x coordinate will not change. So then your one position will be here. If and your rotation, the 2D rotation matrix will appear below here instead of above here. Okay. Are you seeing my cursor, by the way? Hello? Anyone? Okay, good. Because I don't want to mess up too much. Okay, so your the 2 by 2 rotation matrix appears below here instead of the upper block here. But if you look at the case of, okay, what about rotation about the y-axis? So in other words, your rotation about the y-axis must have your y coordinate unchanged, and that should give you what you call the one in the previous matrices to be situated over here. And what happens over here, your block doesn't, well, I mean, your block gets broken up. Okay, so in other words, I have to cross out this thing to be able to see it, and I get the same, the cos theta minus sine theta, cos theta. Okay, so that is easy for you to check, and you can try to do some transformation of some matrices, some vectors if you want. Okay, the general matrix would have to be much more complicated than that, because your rotation matrix, your rotation axis, so far we have limited it in this particular form. So far we either have x-axis, y-axis, or z-axis, but it could appear anywhere. So this rotation about an arbitrary axis, normally, I'm not sure whether I did it over here. Yeah, probably not. Okay, it's quite complicated to describe because there are so many different ways to do it. So essentially, it's just that. So if you are interested in this, in the arbitrary 3-dimensional rotation, then normally these are often described in the literature using what we call the Euler Angles, but I will not do this here, okay? But you can look it up if you want, okay? So this will give you the general 3D rotation about arbitrary axis. However, I should mention that this is not, this is just a convention. So I can use a different translation and give you another general 3D rotation matrix. But I will not go into this at this particular juncture. Over here, I'm just trying to introduce the idea of rotation matrix in general, but at least you need to be able to identify the rotation about x and y and z axis, which is easy to do. Okay, so more or less we covered in a way, in a limited way, of rotation in 3 dimensions. What about reflection in 3 dimensions? Well, since you have 1 dimension extra, then one cannot think of a reflection about a line, but one should be generalizing it to the case of what am I doing here? Reflection. This is reflection about a plane. Or maybe it's not reflection. So it's with respect to, they are done with respect to planes instead of lines. So for example, here is the case of a three-dimensional reflection, and you can see that this block, which has a 1 there, it doesn't change your x and y coordinates, okay, but it changes your z coordinate. So in other words, if I want to draw this, okay, oops, not so nice, draw this again, okay, roughly. So you can see that, okay, this takes a point somewhere here with a non-zero z coordinate reflected about this plane, the xy plane here, and it goes down here somewhere. So this is say xyz, and it goes to xy minus z. Okay, so the matrix will be in this particular form, 1, 1, minus 1. And of course, now you can start to think of, okay, what about reflection about yz and xz? I believe you can actually try to write down what it is. Okay, so I will not show it here, but you can figure out yourself. Okay, finally, for this particular set of notes on lecture 6, I should be introducing to you some idea about special matrices. Okay, one of the things that one can actually try to do is to look at operations for the matrices. So in the case of the orthogonal matrix, you use a matrix transpose. Okay, but one can do an extra thing over here, which is to think of it as a complex matrix. So here, what I'm saying here, you have a matrix M. I'm going to turn this matrix M into a transpose. Okay, so this is what I mean by a unary operation. That means it just take one matrix, transform it to another matrix. Okay, so another unary operation is to do complex conjugate if your entries of your matrix M is complex. Okay, so I will have your what you call transformation here or operation here being just simply equals to that. Okay, so these are the unary operations that you can actually easily have. Okay, but the one which is more important to physics is a combination of these two. Once you have what you call a matrix with complex entries, a much more what you call better operation to look at is what we call a Hermitian conjugate, or sometimes it's called the adjoint. So the unary operations over here is really this thing. The operation Hermitian conjugate or adjoint is given this particular symbol. It's like a dagger there. So M dagger. This you can actually see in quantum mechanics later on. So and that defines a new unary operation, which is a combination of the unary operations of the transpose and your complex conjugate. Okay, and roughly speaking, one can actually think of what's happening here would probably maybe I introduce this later on. Okay, you remember your transpose, one talks about rotation matrix. Then if you have this operation, then one can identify with something like a rotation, but it's a rotation in a complex space. But I will leave this later on. Okay, I will just define first this the dagger operation is simply just complex conjugate, the complex conjugate, and then you do the transpose. Okay, so this is easy enough for you to think of. Okay, with respect to this unary operations, one of the things that we can always try to uh, identify or classify is that you can use these unary operations to define very special matrices. For example, the case where M equals to M conjugate, okay, these are what we call a real matrix. Okay, of course that is simply obvious. You have all this thing equals to the conjugate itself. That means all your entries will have to be real. Okay. So, but you could also have a different. I don't think did I do that over here. I did. Okay. So let me just jump over here a little bit. So the other possibility is to have a slightly different relationship with respect to the complex conjugation operation, is to have, instead of M equals to M conjugate, but instead of that you have M equals to minus M conjugate. Then over here is what we call a pure imaginary matrix. Okay? Plain obvious. Okay, it's just the same thing like we had for complex numbers. If we have Z equals to Z star or Z bar, then this will be giving you Z to be real. Okay, if Z equals to minus Z star, then this will say Z to be imaginary. Okay, it's the same relationship. Okay, the only thing here, you are dealing with array of numbers rather than just a single number. Okay, but let's go back to the way we define this special matrix. We have seen the real matrix and the pure imaginary matrix. So if one looks at the case of the transpose, for example, so if you take a similar kind of relationship where your M transpose equals to M, then we get what's called as the symmetric matrix. And the way to think about this is just to look at the index over here, which tells you about the rows and columns. The first, remember the index, the first index refers to the row, second index refers to the column. So if you have the transpose, remember what is being done in transpose is just interchange your columns into rows and rows into columns. So in other words, M transpose Ij, the ijth element of M transpose, this should give me Mji, right? But now if M equals to M transpose, that means Mij equals to Mji. Okay, so this is essentially saying that you write down the matrix, say over here, let me just do it with a 3x3 matrix, A, B, C, let me do D here, and then E here, and F here. Then this will have to be B, C, and E. So you can see that this triangular block and this triangular block is the same. Okay? So this is the case of a symmetric matrix. Okay, so that gives you a special matrix with respect to the transpose what you call operation. Okay, one could now impose the other condition that we had earlier, okay, for the pure imaginary case. So instead of just m equals to m transpose, then you use m equals to m minus m transpose. And what we have in this particular case, you have the relationship of mij equals to minus mji. Okay, so in other words, over here, for example, if I have this BCE here, then down here will be a minus sign. Okay, and what about here? Now it's interesting to do the diagonal case. So the diagonal case is M11, M1, M22, and M33. But if I set this to be equals to, say, let's say M11, M11 equals to minus M11, and then you do the rearranging of this equation, then you find that your M11 has to be equal to 0. So in other words, your skew symmetric matrix over here should have diagonal, what you call a zero diagonal. Here is BCE again, and this is minus B minus C minus E here, but along the diagonal it has to be 0. Okay. For the symmetric case, it doesn't matter because MII is always equal to MII. It's a trivial thing. Okay, but over here, because of the minus sign, then you find that no, this imposes a condition on the diagonal elements. Another property that we have also seen, we define the orthogonal matrix in such a way that your M transpose has to be equals to the M inverse. So this is another relation that one can actually try to generalize for the case of the complex matrix. Okay, so this we know. Okay, this gives you rotation and reflection. Okay, so now let's go to the case of the Hermitian conjugate. Okay, so what does it mean to have a Hermitian conjugate matrix? Remember, M dagger Ij should be equals to M Ji conjugate. Okay, so now if you start to impose the relationship that we had earlier for the case of the real and pure imaginary matrix, so here is the case of M equals to M dagger. What does it correspond to in this particular case is that your ijth element of M will be equals to the jith element complex conjugate. And this has a name. Okay, this is called a Hermitian matrix, and they play an important role in quantum physics, which I will not elaborate too much. But no, this Hermitian matrix has a place in physics. Okay, and then you do the same with the minus sign. So M equals to minus M dagger. Then we get what we call anti-Hermitian matrix. Okay. Now there is another one, the relationship that we have for the orthogonal matrix. We can also try to impose that in the case of a complex matrix. So if one has your M dagger, remember M dagger is M transpose conjugate. If your M dagger equals to the M inverse, okay, in terms of elements it's given here, but no, it's not so important. But the main thing is if you remember this, then this is referring to what we call a unitary matrix. Now here is where I can make the comparison here. Earlier we had M transpose M equals to I, or M transpose equals to M inverse. Okay, and remember these correspond to rotation and reflections. Similarly, over here you would have some kind of physical understanding of what unitary matrix is supposed to represent. If we have a complex vector space, then we'll talk about that probably in the next lecture, I think. Then your unitary matrix is just like making a rotation, okay, about the inside your complex vector space. Okay, and you can do the same with the reflection in some sense. Should I say that? No, I should not say that. Okay, it's not the same as the reflection. Okay, because reflection still obeys this. Okay, but I can now use the minus sign instead of your plus sign here. So I have an M dagger equals to minus M inverse. Here, if the matrix seems to obey this is what we call an anti-unitary matrix. It has a bit of some what we call physical ideas about that, but it's slightly more complicated from the case of the unitary matrix. But I will not go into too much of that. Okay, so these are some classes of matrices that you're supposed to know. Or a final one. Okay, final one is this. That is the condition of what is supposed to be a normal matrix. A normal matrix is simply a matrix M when it multiplies with your dagger, the adjoint. Okay, it's just the same thing as M adjoint multiplied by M. Have I introduced commutators before this? Anyone can remember? Did I introduce commutators? Because I can't seem to recall that I did that. Maybe not. Yeah. So let me. Seems pretty quiet today. Generally, a product of two matrices is not commutative. Okay, and because of that, sometimes it makes sense to understand what's the difference between these two. So the difference between these two is just simply taking the subtraction there, and this is called the commutator of A and B. Okay, so you have not introduced this, then it's just this definition. Okay, so over here, what it says over here, there is no difference if you multiply your M adjoint or M dagger on the left or on the right. It's just the same, give you the same result. Then it just says that your M and M dagger to have a zero commutator, or M and M dagger is said to commute. Now imagine what this behavior is like. It's just like a number. Okay, your number, if you take even a complex number for that matter, you take two complex numbers, you multiply them, it's the same thing if you multiply in the reverse direction. Okay, so this is essentially a special property, but since matrices in general doesn't do that, then we have a name for such matrix, and this name is called normal matrix. Okay. Okay. What else can we do? Okay. Well, generally matrices do not follow all this. No, they don't belong to these special classes. Okay, the general matrix will be generally they can be in between, if you know what I mean. Okay, so in other words, if we limit ourselves to matrices with real entries, so you consider a real matrix, uh, it can be symmetric if you have that property, or it can be skew symmetric, but generally it will not be either one. Okay, so what happens in this particular case, one can always decompose your general real matrix into two parts. Okay, so what I'm doing here is just a kind of trick. Okay, I'm taking a factor of half in front over here, and then I add the transpose part. Okay, and then the other one, since I add the transpose part, I will take it away from the other half. Okay, remember that I have to have half m plus half m, then I will get back your the whole of m. Okay, but your m transpose gets cancelled out in the end if you do it in this particular decomposition. And then over here, what happens? This whole thing is a symmetric matrix, and this whole thing is an anti-symmetric matrix or skew symmetric matrix. So in other words, a real matrix can always be decomposed in this way into a symmetric matrix and a skew symmetric matrix. Okay. For that matter, you can also do this with the complex conjugate. So in other words, instead of the transpose, you have your m's complex conjugate there. Then basically you can decompose your m into real matrix plus pure imaginary matrix. Okay, that's easy enough for you to see. Okay, by using the same trick. Okay, you add the in this particular case the m conjugate over here, and then minus the m conjugate. Okay, but now we have a new thing, which is now the composite of the transpose and the complex conjugate. We have the adjoint, or the Hermitian conjugate, they call it. So what one can do, if you have a matrix which is having a complex entries, one can also always define it in terms of a Hermitian matrix. So this is a Hermitian matrix over here. So if you take the dagger of this, remember, okay, I should have also mentioned this, just like m transpose gives you m, and then m complex conjugate gives you m, then your m dagger gives you m. Okay, so here you can check that this gives you a Hermitian matrix and this gives you an anti-Hermitian matrix. Okay, and they play a role. Okay, they play a role in physics. Now, what other unary operations that one can actually try to do? Well, one other possibility is to have a square. Okay, you multiply the matrix with itself. That gives you a new matrix, which we call as m squared. Okay, and with respect to this, you can also start thinking of powers of m. So powers of m, say cube, is going to be m squared times m, or this is just m times m times m. So you can see that, okay, I can now start to think of powers of the matrices m. And when you have powers of matrices m, then you can start to think, okay, if I can use powers on matrix, then I can do a power series. Okay, so this gives you a very rich theory in some sense, that one can think about functions of matrices which are represented by power series. So we'll talk about that in a minute. Okay. So here is a matrix, okay, and you can try to find out the square of this matrix, and I've chosen in some way that this is going to be a special type of matrix. Okay, we will define what these matrices are in a minute. Okay, they have names. Okay, so here if you try to take this matrix M and you take the square of that, you suddenly get this equals to the negative identity matrix. Okay, that's interesting. And once you have that, when you try to get higher powers of that of M, sorry, so for example M cubed, you know that it's going to give you minus M because M squared gives you minus I. You multiply minus I with M, you get minus M. And then when you try to multiply M to the fourth, powers of M to the fourth, remember that you have minus M squared in that particular, in that particular case I would have minus M squared for M to the fourth, but M squared is already minus identity, so I will get identity. So in other words, you can see that, okay, this sort of gives some kind of oscillatory behavior in terms of the powers of M. Okay? And for that, those kind of matrices, they have certain properties, and you probably will see this in quantum mechanics. For example, you'll see, we'll talk about Pauli matrix. Pauli matrix represents spin in quantum mechanics. So they have some specific behavior that allows you to do having to be able to see some nice properties about them. Okay. So let's start to introduce some names, some labels. If your M squared equals to M squared equals to I, this is what we call an involuntary matrix. I think if I'm not mistaken, there's also sometimes called anti-involuntary, but no, probably it's not standard enough. So M squared equals to I. If you have the case that there's a power of M that it returns you back to the matrix M, then we call that matrix M to be periodic. Okay, and the period is determined by the powers over here. So here is, suppose that this is a power of k plus 1, then essentially you have a period k. So in other words, essentially what happens is over here, you think of this okay, and then at the point of M to the power of k is not equals to M yet, but once you go to the mk plus 1, it returns to M. So you can see that this is periodic in this sector. Okay, so here so this one is mk plus 1, and the next one is M squared, which is equal to mk plus 2, and so on. So it sort of repeats itself again and again. So if one looks at the previous example, what would be the period of this particular matrix? Anyone? Somebody? It should be. What's the period of this matrix? Is the class still with me? Somebody? Yes or no? Okay, you're still with me? Okay, good. Can anyone give me a number to tell me what is the period of this matrix? 3, 5. It should be 4, okay? Can waste too much time there. Because the next one will be, no, it returns back to M. Okay? So in other words, what happens is you have this cycle, M minus I minus M, I, and then returns to M. Okay? And so on and so forth. Okay, the other possibility is to have the possibility of a period of essentially period 1. Okay. M squared equals to M. And for this, we call this particular type of matrix to be idempotent. Okay? So these are sometimes plays a role in a way this idempotent matrix. Okay? One of the things that you'll see later on is the idea of projection. You project onto some direction or some particular usually in terms of direction. When you project it twice, okay, you project square them. This is just the same as a projection the first time. The second time will not, since it's already inside in particular direction, you project the second time, it's still inside that same direction. So this idempotent matrix has this what I call similarity with idea of projection. Okay. Another one is when you have suddenly when you take powers of your matrix M, and suddenly it gives you a zero matrix. So 0 here means 0, 0. Okay. So all the elements inside this matrix is 0. And it does that for a particular power, in this case power P, then we call this as a nilpotent matrix of order P. And again, there are some usage of this. Probably when you do more abstract algebra, then you probably should be able to see why nilpotent is going to be important. Okay, okay, let's now try to finish this off. I think that's about it here. So let's try to finish this off with the idea of function of a matrix, since we can do powers now. So I can start to think of taking a power series. So for example, using the exponential. Okay, what is you remember what exponential is supposed to be? This is just x to the n over n factorial sum from n equals 0 to infinity. I can do that with a matrix, since I know how to take powers of m. So I'll be able to find out what's the exponential of n. Okay, so it's just simply defined in this particular way. Okay, so let's consider the case of a matrix. Okay, in this way, I'm going to use this particular example first. Let's consider what these matrices are. So if I simply collect example 6.4, what's that? Forgotten now. 6.4, oh, this one, this matrix, okay? So I'm referring back to this matrix, and I'm taking the exponential of that. I'll be able to write down, okay, remember that, okay, let me just write it down. Your m squared equals to minus I, your m cubed equals to minus m, and your m to the fourth is m, I. m to the fifth is. So I can start to, okay, I'm going to collect those products of m, those powers of m that gives you something which is proportional to the identity matrix. So I collect in this way. And then I collect those powers of matrix m that gives you m, whether it's plus or minus m. Then I have this. And one can actually see, okay, this looks interesting because this is just the power series of cosine. And this is just the power series of sine. So I can now write this in a much more compact way, that this is just cos ki times sine km. Or if I write in terms of matrix, the matrix that's been given, then it will be equal to that. So sometimes you'll be asked to evaluate functions of matrices in this way. Okay. So let me go to the last one before I finish off. So this is maybe I should leave that because this is going to be important later on. I'll leave that. So I'll stop there for today, and I will continue next week. And remember, we still need to replace the missed lecture on Monday somehow. I hope you can discuss this. When precisely can you do this? Okay. All right. I'll stop there, and I will take the attendance now. Is there somebody in chat? Okay. Okay, so that's done. So I think that's where we will stop this lecture. So thank you, everyone. Okay, bye.